Yesterday afternoon, and please consider your time would be appreciated if you take the time to do that. What have we been doing the last couple of classes? Well, we've been introducing something called simple harmonic motion, right? The ideal spring went back and forth forever. The simple pendulum oscillates forever. Those oscillations, nothing ever stopped them. They just kept going forever and ever and ever, right? Now, in reality, if you were to set up a spring and release it, would it just keep oscillating forever? No, some more no's. Anyone yes? I'd like to set a spring if you do, but no, right? In reality, if you released a spring, it would eventually come to a stop, is what we would think would happen, right? So, in fact, this simple harmonic motion stuff is very good for getting our foot in the door to what physics is all about, but it's not a very real system when it comes to something we would see in engineering design or something like that, okay? In reality, we have friction that slows things down. Other dissipative forces that slow things down. That's what we're going to be introduced today, okay? So simple harmonic motion, we had something like an ideal spring that just kept going forever and ever. In reality, it ain't like that, right? We need to add damping because things slow down over time. So we're going to call these frictional forces, broadly speaking, damping. And essentially damping will slow down our oscillations to a stop. Okay, and damping can be very important, especially stuff like construction, like building bridges and skyscrapers and stuff. You have to appropriately damp these things so they don't oscillate out of control when you build them, right? So very important engineering topic as well. All right, so what are we going to do to introduce damping? Well, we're going to start with that ideal spring model. We'll just have our ideal spring to begin with. Then we're going to add a damping force. All right, so we're going to have some damping force. The one we're going to use is kind of the conventional one. We'll use some viscous fluid that's going to slow down the motion. But it could be anything causing damping to our system. And we're going to add this by adding an additional force acting on the mass on the spring. Okay, so let's take a look at what our picture looks like. So remember, no gravity. I'm not talking gravity yet. We just have a spring constant K, with a mass on the end of it. Now this thing's going to oscillate back and forth, and we've attached this thing here that's immersed in some liquid. So each oscillation, this liquid's going to slow us down, and eventually we're going to come to a stop. All right, so this is our damped spring system, and basically what we want to do is write down an equation of motion for this system, solve it, and see what the predicted trajectories are. Right, so it's the same basic rationale as the last couple of classes, just a bit more complicated now because we have an extra force to consider. What is that force? That's the damping force. Okay, so if we have a 1D situation, like the ideal spring in the x direction, we're going to have a force that is damping us, that is slowing us down, and that force is this equation 2 here. So we have a negative sign times a constant b times the velocity. So remember, Hooke's law was negative kx. It depended on position. Our damping force depends on our velocity. So if we have a bigger velocity, there will be a bigger damping force. We'll be more aggressively slowed down. Now, the negative sign, this is always opposite to velocity. That's going to ensure it brings us back to the origin, this slowing of speed. The force, as t becomes large, we're eventually going to come to a halt, essentially, because of our damping force. This constant B is called the viscous damping coefficient. It's just some parameter telling us how viscous the fluid is. In other words, how strong is this frictional force? Bigger constant, we're gonna have a stronger force slowing us down. This is our damping force, and essentially, we just got to take this, go back to Newton's second law, and plug it into our spring model. So let's go back to Newton's second law. So that equation at the top, that's our Newton's second law. F net equals ma, like usual. Now, we have two forces acting on our mass. One's from Hooke's law, the negative kx. One is from the damping, the negative bvx. So we have max equals those two forces, and this is how we're going to build our equation of motion. Remember, before we related a to x with 2 time derivatives, right? Acceleration is 2 time derivatives of position. Turns out we can also do that for velocity, right? Velocity is 1 time derivative of position. So we can replace a and b with derivatives of x. That will give us a differential equation where x is still the function we're solving for. That makes sense, right? We want to predict the trajectory of our spring. So we want to predict as a function of time, where is the mass as a function of time in the x-axis, okay? So that's what we're doing here. We're building an equation of motion to predict where the mass is. That would be x that we've solved for. So we plug in these derivatives. What are we left with? We're left with a differential equation representing the damped oscillator system. Okay, so this is the damped oscillator equation of motion, where we have 2 time derivatives of x related to 1 time derivative of x related to x. If we can solve this for some function x of t, we will have a prediction for how this thing will behave. So it's the same basic rationale as when we did the ideal spring. We just have an extra term now in our differential equation. Okay? All right, so what about the coefficients? B over m, k over m. We don't have to do this, but sometimes we rewrite them, or we will, for the most part, rewrite them in terms of other things. Remember, k over m is related to our frequency for the ideal spring. Let's see what these coefficients are that we're going to call, okay? So the square root of k over m, it's no longer our angular frequency, but it is important. It's something we call the natural frequency, okay? Omega naught is going to be the natural frequency. That's basically what the frequency would be if we had no damping, right? So that's the frequency of the ideal spring. That's the natural frequency of the system if we had no friction or damping or anything like that. The other coefficients, B over M, we typically rewrite as the damping coefficient. Call it gamma, and we just replace everything in front of that dx dt term with gamma, okay? This will give us a general form for the damped oscillator equation of motion. We plug those in, and here we have it. So this is the general form of the equation of motion for the damped oscillator. We'll see this for other systems in the course. Same form of differential equation. Kind of like simple harmonic motion, anything that had that form of equation, we could use the simple harmonic motion equation, say that it follows simple harmonic motion, just anything that's oscillating. Similarly, anything that oscillates to a halt due to some damping like this, we call the damped oscillator. So it could be the spring system, it could be the other stuff we'll talk about. Now, there's a big difference here. There's a big difference when we talk about damping. Remember, for the ideal spring, we solve the equation of motion. It just goes back and forth forever according to some cosine function. The damped oscillator is quite interesting because we have one equation of motion and three different types of motion that can happen. This is experimentally verified, and it kind of magically happens in the math too. It's the very cool thing about this fundamental physics. We have something that isn't intuitive, that three different motions can occur here, and that's also what we see in reality. Okay, so let's look at these three different types of damping motion. Oh, first let's talk about them. Why do we have them? So, what we'll see here in a bit is the angular frequency for the damped oscillator is given by this expression. The damped oscillator has an angular frequency, square root of the natural frequency squared minus the damping constant squared divided by 4. Okay? This is our angular frequency. What happens when we have a negative value under a square root? Right, what happens? What do we have to do? There's a negative under a square root. Yeah. It becomes imaginary, right? The square root of -1 is I, right? The imaginary I. And essentially, if we have a negative under here, or a positive under here, or a 0, it impacts the solution to the equation of motion, giving us different behaviors, okay? So there's three scenarios. We could have a real, 0, or imaginary value for omega here, just based on, is this bigger than this, or is this bigger than this, or are they equal? And that, in reality, gives us three different visualizations for what the motion will be. So let's talk about these three cases. The first case is something we call light damping. So there's our omega. If the gamma squared bit is less than the omega naught squared, we have a positive value under the square root. Omega is a real number. We say that it's light damping. Okay? Light damping is the one we would expect naturally, that our spring will just kind of do this and oscillate to the center. Okay? So light damping is sometimes called under damping. I put both terms because in other engineering courses they might call them different names, but it's the same thing. Light damping or under damping is the case when this stuff is bigger than this stuff, so this is real. What about heavy damping? So heavy damping, this is when this stuff is bigger than this stuff, so we get a negative under our square root. We have an imaginary value for omega. Okay? This is known as heavy damping or over damping. And basically, heavy damping is kind of like that, you know, the board game, you collect money and stuff, Monopoly, right? When you go straight to jail, you don't pass go, it's a real rough card to get. Anyway, heavy damping is kind of like that. You just go straight to 0. You don't oscillate anymore. You just go all the way back to the equilibrium position exponentially, okay? There's no oscillating back to the center with heavy damping. You just immediately go to 0. You don't get to collect anything on the way. It's a real rude thing to get in a game of Monopoly. But anyway, critical damping. So critical damping is the case where those two values are equal. So we get 0 for our angular frequency. In the case of critical damping, the motion goes straight to 0 as fast as possible. So it also exponentially goes to 0 as fast as possible in the case of critical damping. And basically, depending on these parameters in our system, what we will see in reality could be quite different. Let's take a peek at the graphs. So we have over damping or heavy damping, critical damping, and under damping, otherwise known as light damping. Depending on which one of those situations we have for our system, the motion, x versus t, can be very different. So in the case of heavy damping, we go straight to 0 according to some exponential decay. In the case of critical damping, we more aggressively go straight to 0. And in the case of our light damping, this is what we would maybe expect would happen. We just oscillate back and forth, getting slower and slower, or smaller and smaller amplitudes until we come to a stop. Okay, so these are the 3 types of damping motion. And it all is predicted by the same equation of motion. So just depending on the parameters in our system, we will have different solutional forms. Now, it's just one solution method. Those solutions change depending on those parameters. So it's one method to solve the differential equation, 3 outcomes based on if you have the real or imaginary values. So I'll go through that here in this class. Oh, I did it again. Nice. Right? You like the gifts yet? I like the daily gifts. In the back, like the gifts? No, a couple nods, a couple thumbs up, a couple people just looking at me. All right. We'll assume at least 10% of the class enjoys the gifts. But we'll take the poll later. It's going to be 90 here. You're going to grow to love them. So here's a nice one here. This is the ideal spring. So the ideal spring, here's its trajectory down here. Here's its phase space. So the ideal spring oscillates back and forth forever, and it has a nice ellipse in the phase space. Okay? So this is the one we've been getting used to the last couple of classes. How do you think this is going to change now for the damped oscillator for light damping? Yeah? A spiral inwards. Very good, right? As this thing slows down, we predict it would spiral inwards. Let's take a look at the damped oscillator. So watch here, down at the bottom. Oh, there we go. Nice. Nice. This is how you can do art with physics, right? You just go to the phase space, find a nice system, and see what happens. So you can make a nice little spiral here for your phase space. And we see our trajectory declines as a function of time. The amplitudes decline in a predictable way that we'll talk about as well later in the class. But anyway, here's the damped oscillator picture. And I think I have one more. Uh-oh. All right, we got to scare the computer again here. Make it think we're going to shut it down. Okay, let's see. Did that do the trick yet? It did. It just knows it's up to no good, right? Anyway, yeah.
Are these GIFs available?
Are these GIFs available after? I was thinking maybe I can make a folder or something and post them somewhere. But they're a good way to visualize kind of what we talked about during the lecture stuff. Yeah, so if you remind me at some point, I will put these GIFs in the folder somewhere, maybe I can look something. But this is the last one for today. This is a nice one. We have an ideal spring and a damped spring. This is what we would see when we look at the lab, the difference if we had 2 of these models. And we can see if we start from the same point for each of them, how their trajectories change with time. So you see very rapidly, the damped one can decline relative to the ideal one, and we get a real system here to kind of come to a halt pretty quickly. So anyway, that's it for our gifts this week. Thank you. Yes. Yes. Oh, this is going to be a sweet section, I know. We've got to get ourselves a smaller class. Seriously. Stuff and beach balls going around in it, I don't know, dude, but we've got to get a smaller class. Yeah. What's the phase space for the damped one? Or just in general? It's a different point of view, exactly. It's like the phase space is just a different way to look at the motion. Here we're looking at x versus t, whereas the phase space, we're looking at v versus x, velocity versus position. So it's just a different way of interpreting or visualizing motion. Okay. Let's get back to the little lecture here. Okay, what about other stuff? Is it just damped springs? Well, usually when I ask the rhetorical question, the answer is no, right? Or yeah, I don't know. Sometimes rhetorical questions have a yes, sometimes it's a no. But in this case, it's a yes. There is other stuff that we can have a damped system for. One, imagine we have a real pendulum. This thing's eventually going to come to a stop, right? So a real pendulum would be like a damped pendulum, right? What about circuits? Later in the course, we'll see that the LRC circuit has the same equation of motion as the damped oscillator. So there's different areas of physics where this damped equation of motion appears. We're today just going to talk about the pendulum. Okay, so the pendulum. Last class, we found the simple pendulum equation of motion using Newton's second law for rotation. That is the net torque equation. So it might kind of seem intuitive that in order to add damping to the pendulum, we need a damping torque. We need a torque which is going to damp the system over time. What you'll see with these models, if you understand one of them, all of them start to make sense. Because look, the damping torque is just the same thing basically we added as the damping force. We have a negative sign, some damping coefficient, and then the angular velocity, d theta dt. Right, so instead of the linear velocity for linear force, we have the angular velocity d theta dt for the damping torque. Okay? So again, we have a negative torque. This is opposite to the angular velocity, which is going to slow down our pendulum. And in a very similar way to how we set up the damped spring model, we can go back to Newton's second law for rotation, add this damping bit, and have a model for the real or damped pendulum. So what does that look like? Well, for Newton's second law for rotation, we had that equation up there in equation 19, last class. This class, we add the damping torque. All we do is add that contribution to our net torque equation. Right, so we just add the damping torque term, and then we have an equation of motion for the damped pendulum. So we have our derivatives of theta, two derivatives, one derivative, but we still have that sine term like we had last class. Now, these coefficients we rewrite in terms of gamma and omega naught for all of these damped models. So basically, whatever's in front of this d theta dt here, that's what we called gamma before. So gamma is b over ml squared. I realize that L randomly changed on this slide. I forgot to change this one. I switched to capital L just because it's a bit more L-like, right? This is, anyway, I don't know. It's alphabet humor, but basically we have a gamma here for the b over ml squared, and then this is the g over L. That's what we had for the simple pendulum last class. That's going to be related to the natural frequency. So we can rewrite those coefficients. We get an equation of motion here, but we have that sine term. Remember, this is the damped pendulum for full motion. What did we do last class with this sine thing? What did we say? Yeah? It was equal to theta. When? When is it equal to theta?
When it's really small.
When the oscillations are small, right? So sine theta is equal to theta if we keep the oscillations nice and small. That's called the small angle approximation that we talked about last class. So we can replace sine theta with theta and get something in the exact form as what the spring model does. So that's what we do. We use the small angle approximation. We get the damped oscillator equation of motion exactly like for the spring model. From here, all the same rationale applies. We could have light damping, heavy damping, critical damping, the same forms of the solutions. It's just the same mathematical model, just with a different physical interpretation. Okay, so this is the damped oscillator, just like the damped spring model. Right? So I guess the main point here is, just like simple harmonic motion could be a bunch of different things, damped oscillations could be a bunch of different things. And when it comes to engineering, damping oscillations is very important. Right? This is how we make sure our bridges don't collapse when the wind blows at the natural frequency of the bridge. Right? And we'll talk about that on Monday. Okay, some important notes here. So again, just like for simple harmonic motion, we have different physical systems with the same mathematical model. You can start to see why our foundational physical laws, such as Newton's law, are so powerful. It's just one rule of nature. We find all these different scenarios to apply it, and we get all these different equations of motion that can predict just what's going to happen, right? And this is the ultimate goal of physics. Have a relatively small number of general laws for which you can predict everything that we see, right? And we start off with stuff that's as easy as possible when we introduce this stuff. Okay, what are we going to do next? So next we're going to talk about the rationale behind why one equation of motion can lead us to predict three different types of motion. Okay? Now this is pretty important stuff for your degree in general. Most of it you'll learn in second year when you take a differential equations course. I'm going to go over kind of the basic idea. You won't have to actually solve a second order DE from scratch in this course. I'll just give you all the functions of these three types on your equation sheet, but it's important to understand what we're about to talk about here. Okay, so here's the basic idea. We have a differential equation that relates derivatives of a function to the function. Last class, we talked about how, well, what's a good function where the derivative of it is itself? The exponential function, right? So the method for solving these differential equations involves taking advantage of the exponential function's ability, which is to be the derivative of itself. So what we can do is we take a test solution, x equals e to the RT, and plug it into our equation of motion. We know that two derivatives of this will be related to one derivative of this, which will be related to this. How do we make sure that our solution equates everything perfectly? Well, this little r here, when we take the derivatives, it will plop out using the chain rule. Then we just solve for what r has to be and plug it back in. That's your second year ODEs course in a nutshell. Okay, so there's more to it than that, but that's pretty much all of second year ODEs when it comes to this type of differential equation. Now, what do we do? Let's show. Here's our equation of motion. We take this test solution, exponential, plug it in here, take two derivatives, plug it in here, take one derivative, and then we cancel the exponential bits. What we're left with is a quadratic equation. This quadratic equation is I don't know if I want to say famous one, because probably no one you know outside of here will have ever heard of it. But within math and engineering circles, the characteristic equation is fairly famous. This is what we solve to figure out what the solution to our differential equation will be. How do we solve a quadratic equation? Oh, I spoiled it. It's on board. The quadratic formula, right? You can just use the quadratic formula and find the two roots that solve this equation. Now, we have these two roots. We can plug them back into the exponential function with free coefficients, and we have our solution to the differential equation. That's literally all of second year ODE. I shouldn't downplay that course. There's more to it than that. But that's pretty much second year ODEs NMM227. Why do I know the course code? Anyway. So, we've solved our characteristic equation. What's the solution to our differential equation? We just need an exponential term for each one of the roots. So we plug in the first root, plug in the second root. They have arbitrary constants. That's where this stuff comes from. Now, remember, we had two initial conditions. For those of you who've done tutorial, if not, this will make sense when you practice this next week. Two initial conditions, which we use to solve for the amplitude and phase constant of simple harmonic motion. Same basic idea here. We need two initial conditions to solve for these two unknown constants. Now, where does the cosine stuff come in, like we talked about for simple harmonic motion? It's something called Euler's formula. This formula is related to people thought this formula was magic back in the day. The complex exponential function is related to cosine and sine functions according to this formula here, okay? So if we write our roots in terms of some complex coefficients, and this is exactly how you do it for the ideal spring as well, when you plug them in to the exponential, you can replace the complex stuff with cos and sine. That's how you get the cosine one for the ideal spring. Why am I going through this here? Well, you notice what's in front of these complex i's here is exactly what we claimed omega was before. We said omega was this stuff. And the other thing we said was that if omega is real or zero or imaginary, we'll have three different types of motion. And this is how we can explain it. If this is real here, then this is real, this is complex, we can convert this to a cosine function, we get the predicted light damping cosine behavior. If this is imaginary, we have imaginary times imaginary, I squared is -1. We cannot use this. We're stuck with decaying exponential functions that predict the motion goes right back to 0. And if this is 0, this stuff is all 0. Again, we can't use Euler's formula. We have decaying exponentials. So the point I'm trying to get at is we just have one solution here. But we can write it as exponentials or cos or different forms depending on what this ends up as. And that's three actually different motions you can see in reality. So it's pretty cool stuff that the method for solving these equations of motion naturally predict different types of motion we would see in the lab. So it's all based on this thing here. It's all based on this omega. Light damping or under damping. If this is real, then we have light damping, we oscillate to 0. If this is heavy damping, well, we just have a decaying exponential function, goes straight down to 0. Critical damping, we go down super fast to 0. Okay? So this is the three different types of motion. It's all based on the parameter system. Yeah?
Or on the previous slide, when gamma squared over 1 is minus omega squared, then that's a real function. Because there's also an I sign, so what would that affect?
There's a bunch of math to get from here to what we have for the ideal spring.
Because there's also an I sign part, so wouldn't that also part?
It's more because we have to plug in our R1 here and our R2 here. We get a bunch of terms. We have to combine them using identities and stuff. It's a long process to get to the final formula solution. We can talk about that after class if you're interested. Okay, so graphically again, we have three different types of motion, three different types of predicted behavior from one equation of motion. It's very cool stuff. This is the goal of physics, right? We have one general law. It predicts a bunch of possible things that can happen. That's what's happening here. As I said, you don't have to be able to solve a differential equation from scratch and get the final functions. I'm just going to give them to you, so that's what we're going to focus on now, is going through the functions that represent each of these motions. Let's start with light damping. Light damping, we have A, the initial amplitude, times a decaying exponential, times the cosine function. So what we have here is the amplitude of the cosine function is a decaying exponential. That's what those dotted lines are. That tells us that the maximum amplitude decreases as a function of time. And the cosine bit tells us how we're oscillating within that envelope. Okay? So this is why for light damping, we end up coming to the center here. We have a function which literally predicts that. As time goes on, the amplitude gets smaller and smaller until it gets to 0. All these functions for light, heavy, and critical damping will appear on the equation sheet for the tests and stuff. Okay, let's talk about something interesting with this light damping. Pretty cool fact about light damping. The light damping solution, we have some amplitude that changes with time. So that's our A times the decaying exponential, times the cosine stuff. Okay? When we check out what is the ratio of one amplitude to the other, maybe I'll go back and we can look at this plot here. Here we're at a maximum amplitude. Look where this little hand is. A. I'm waving. Nice, thanks for waving back. So here's the maximum amplitude. Here's the next maximum here after one full period. Something pretty fascinating happens when we compare this amplitude to this amplitude, or this one to this one, or this one to this one. How would we do that? Well, for two subsequent amplitudes, let's say an and an plus 1, so just pick any amplitude and then the next one, we would plug into our function some initial time, let's say t naught, and then we would plug into our function that same initial time plus t, one full period later. That's when the next amplitude is going to happen. So when we plug in those time values, we can divide our amplitudes. So any amplitude divided by the next one, you do some math, you get a super simple relationship that is a constant. So it's an interesting fact about light damping. The decline from one max amplitude to the next one, or this one to this one, or this one to this one, is always a constant value. So if you divide anyone, you can pick the first and the second, the fifth and the sixth, the 1 millionth and the 1 millionth and 1. You divide any of those, you will have the same constant decline, okay? Now, you can take the natural logarithm to separate this. This is known as the logarithmic decrement, okay? And this is basically an indication of how rapidly the oscillations are decaying. So, cool fact about light damping, it's very predictable how it's going to decline from one cycle to another according to this division here. What else about light damping? Well, phase, right? It's a spiral, very different than when we talked about simple harmonic motion, which was just a perfect ellipse. Here we have a spiral where the motion spirals into the center. So light damping, pretty cool stuff that we can talk about. It's kind of like the oscillations before, where we just oscillate to the center. Now let's talk about the other two. Heavy damping. Here's the solution. So for heavy damping, we have omega imaginary. You can think of heavy damping as being the lazy solution. The heavy damping solution is literally if we just plugged in our roots to the characteristic equation into the exponential function. But we can't use Euler's formula. We're just done immediately, okay? So you take the roots to the characteristic equation, sub it back into e to the RT, you have two roots, you're done. Here's the heavy damping solution. Now, some students had some good questions in the first class. Why does the heavy damping one not go faster than the critical damping? Because the damping parameter is bigger for heavy damping than it is for critical damping. Well, one of the main reasons for critical damping, we lose this positive exponential bit and this negative one. We end up with just negative exponentials which decay faster. That's one of the reasons. We'll get to the other. But basically for heavy damping here, we have overall negative or decaying exponential functions with two unknown constants, C1 and C2, that will predict the motion. If we have initial conditions, where did we start? How fast were we going? We can specify what is the value of C1 and what is the value of C2, no different than you will in your first tutorial for the ideal spring. Okay, so, and really throughout modeling stuff in physics and engineering, if you write down a differential equation of motion like you've been doing, you always need some initial conditions to figure out this particular solution. And it's the same basic process every time. Okay, here's critical damping. For critical damping, omega is exactly 0. In other words, all of that square root stuff in our roots of the characteristic equation goes away. We have what is called a repeated root. Okay? This might be a flashback to grade 10 or whenever they do the quadratic formula. We have a repeated root here. So both R1 and R2 are the same value. We're not going to get into why in this course. I mean, the basic idea is because we need two unknown constants. But basically, when you plug in a repeated root, you only have one value for your exponential. So you just have one term. For these differential equation solutions, for a general solution, we need two terms with two coefficients. So when you have a repeated root, there's a way to find the second one. The second one is just the same thing times t in this case, and in a lot of cases. Again, I'm spoiling your whole second year ODUs course here today, but basically, when you go to solve these in second year, you'll learn how and why to do this. Off the top of my head, I don't even remember how to find that t there, but you will in second year. Then you can tell me. You may be, oh, I figured it out, and I'll be like, word. Okay? So anyway, here's our critical damping solution. This predicts that we go to 0 much faster than the heavy damping solution. All right? And what do we do with those three functions? That's what this was. That's what this was from the beginning. This is the x of t for light damping, critical damping, and heavy damping plotted on top of one another. Okay? So when you solve your equation of motion, you can get these three scenarios, three functions, plot them, and that's how you understand damping motion. Okay? So I think we should just take off for the weekend here, eh? Peace out. See you Monday.